everyone, welcome to our video. We are Team Codeblenders. Our team members are Francis, Shiqi, and Tongxin.
This is Tongxin, by the way.
This video is a summary of our Bengali.AI handwritten grapheme classification project. Now I will take you to our project webpage and walk you through our project. So as you can see, this is our project web page. We have links to our team members' LinkedIn as well as the links to the Kaggle competition. So I will start with the introduction of this competition as well as the background and motivations behind this project. So this Bengali.AI handwritten grapheme classification is a Kaggle project held by a non-profit company called Bengali.AI. This project hopes to improve the approaches to Bengali handwritten grapheme recognition. Bengali is the official language of Bangladesh and the second most spoken language in India. Considering there are millions of people using this language, there is actually significant business and educational interest in developing AI that can optically recognize the image of the handwritten Bengali graphemes. Bengali has 49 letters in its alphabet. There are also 18 potential diacritics or accents. The dataset is also provided by Bengali.AI. We are given the images of Bengali handwritten graphemes, and we are required to separately classify 3 elements in the image: grapheme root, vowel diacritics, and consonant diacritics. Shiqi will go over the EDA part of our project as well as the baseline model. Francis will talk about the enhanced model as well as the predictions and outlook. By the way, we want to say thank you to our classmate Shayong for providing this amazing handwritten Bengali picture for us to use as our project background, like right here.
Hi, I'm Shiqi. So I will briefly talk about the EDA visualizations and introduce our baseline model. So our data set actually contains 2,000 training handwritten Bengali grapheme images. It's particularly challenging because each Bengali words has its own grapheme roots, vowel diacritics, and consonant diacritics. And in total, there are actually 168 classes of grapheme roots, 11 classes of vowel diacritics, and 7 classes of consonant diacritics in Bengali languages. And below are 3 plots that shows the distributions of class values in our dataset. As you can see in this plot, it shows the most frequent 20 classes of grapheme roots, and these pictures shows the all of the class of vowel diacritics, and this one shows actually our classes of consonant diacritics. As we can see in those 3 plots, grapheme roots and vowel diacritics are distributed in a very smooth way, and we can see that like in consonant diacritics, there's a big gap after the class 0. There's another visualizations we can see right here. When we further explore into our actual handwritten of Bengali words, we actually find that many graphemes images we were provided did not fit into the center, or even the picture got cropped. So as you can see in the sample images below. More specifically, their background are not very clear, showing that there's a noise on the images, and we need to pre-process the dataset using EZA whitening technique in order to eliminate the noise. As you can see in those plots, their background are not actually completely white. So below are visualization of the top 10 and last 10 classes of grapheme roots. So here's the top 10 classes, and here's the last 10 classes of grapheme roots, as you can see. Also, we also plotted the sample images of all classes of vowel diacritics and consonant diacritics. One challenge we might encounter in the future model training process is that the dataset actually does not have sufficient training points for the last few classes in the Grapheme roots. So the classification in the final model might not be as accurate as the top classes in the Grapheme roots. To address this noise issue, we did build a multi-output generator in order to randomly rotate, zoom, and shift images for creating more training data, and we also did ZCA whitening for that. In this way, we boost the performance of our CNN model drastically. Let's go back to our baseline model. So we built our baseline model including using convolutional neural network, and the model includes 2D convolution layers, batch normalizations, max pooling, and dropout in order to eliminate the risk of vanishing or exploding gradients problem and overfitting. And we adapt the Kaggle notebook from Kashuashan to build our baseline model. These 2000 training handwritten grapheme roots are actually stored separately in 4 parquets. So for our baseline model, we only trained the first parquet in issue of the runtime. So we obtained the reasonable scores for our baseline accuracy scores. And also, we're gonna show you the TensorBoard of our baseline model. TensorBoard actually keeps track of model training histories and plot metrics like loss and accuracy scores. And the picture you see below is our scalar dashboard, which actually shows you how the loss and metrics change with each epoch. You can use it to track training speeds, learning rate, and other scalar values. And in this plot, the orange line keeps track of the training process, and the blue line shows the history of the validation datasets. As we can see in both accuracy and loss plots, as epoch increases, those score actually becomes more and more stable, and it actually shows that like we do not have overfitting or underfitting issues during the training process. And next, Francis is gonna talk in detail about the model we used in our final submission.
Hi, I'm Francis. Let me walk you through our final model. In our final model, we firstly resized our initial image data into 64 by 64 dimensions. Here is our resized model. Here shows our main final model section. We input the resized image into these convolutional layers and applied ELU activation function to the matrix. We added as many convolutional layers as possible until the result was satisfied. We also performed batch normalization to reduce the dependence of gradients on the scale of the initial values, and dropouts to reduce interdependent learning among the neurons in the network. We also used the max pooling to reduce dimensionality size. Eventually, we flattened the output and fed it into a fully connected layer to classify each image into 3 parts. We tried to improve our baseline model in terms of firstly increasing the accuracy scores, and secondly try to speed up the training process. The first thing we did was trying to change the activation function. We eventually found that ELU performed the best among all the activation function. Compared with ReLU, it avoids the dead neuron problems that would only output 0. And in this diagram, we can see that when the output is negative, we still got these gradients that is very close but not equal to 0. Therefore, we can still deliver the information to the next layer. Beside the activation function, we also change the learning rate from constant value to learning rate scheduler, which consistently decreasing the learning rate during the training process. We tried time-based decay, step decay, and exponential decay, and it turned out that the exponential decay gave the best score. Here shows the learning rate scheduler callback, and we initially pick a very small starting learning rate, and then we use this Kira's exponential decay function, choose the decay step and decay rate to be put into the callback function. Furthermore, we applied a boosting algorithm into the training process. It turned a weak model to a stronger one by fixing its weakness. The algorithm works by initially training a model on a small dataset and then taking all of the training data to test the model. When we train the first model, we address its deficiencies, which allow us to train the subsequent model from baseline instead of from scratch. During the baseline model training process, we saved the model weights for the final training. For the subsequent model training, we try to freeze the convolutional layers, which is shows here. And the training time was even shorter, but the accuracy is lower than the score from unfreezing the layers. Here is our final results. The root improved the most and the consonant improved the least. This is because the root has a way large size of classes and the consonant only has 7. Therefore, it's more difficult to improve the consonant data anymore. And this is one of the results of our Kaggle entries, and we are still trying to improve it. Here are some shortcomings of our model. The ILU activation function is slower to compute than the ReLU function, and it is inefficient to train large dataset on the model. Another shortcoming is that the dataset does not have efficient training points for the last few classes, and the classification might not be as accurate as the top 10 classes of our roots. And eventually, the boosting method we used is very random, which means that it gives random results every time when we're training. Therefore, we might not be able to get the optimum score all the time. We also thought about a few potential methodologies to improve our model. Firstly, we could perform the confusion matrix on our result to evaluate our predictions. Secondly, it is feasible to modify our deep learning model structure to improve the accuracy. And eventually, we can apply transfer learning process to further train our model, such as the fully convolutional networks and the efficient net. For the outlook of this project, the model can also be applied to improve the recognition of handwritten characters in other languages, using the concept of transfer learning.
Okay, guys, thank you so much for watching our videos. And if you have any questions based about our project, feel free to contact us through our emails. Thank you.
Thank you.
Thank you.